In this recording, I will investigate what happens when we differentiate a Laplace transform. Let's suppose that we start with a function, little f of t, and we know its Laplace transform to be capital F of s. I've written that here. What does this actually mean? Well, the Laplace transform is defined by use of an integral over t involving an exponential. We could write down that definition. Capital F of s is the integral from 0 to infinity, little f of t, e to the minus st dt. And normally somewhere we record that s is assumed to be positive. The reason for that is that we require that the integral converges when t gets very large. Now the right-hand side of this expression contains t, but only as an integration variable. Once the integration is performed, we would substitute the limits. In that case, t will disappear from the expression altogether, and only s will be left. Hence, it's sensible to regard this as a function capital F of s. But now, capital F of s is a function in its own right, and so it has its own gradient function. There's no reason why we can't differentiate it. But the question is, can we find a sensible interpretation? Is it useful to do this? Well, let's just start and see what happens. df by ds would have to be the same as d by ds acting on the integral from 0 to infinity, f of t, e to the minus st dt. Now t and s are completely independent objects, so it's quite possible to sneak the d by ds through the integral sign without it getting noticed. The only place where the d by ds is going to have an effect is when it meets something depending on s. Hence we can write df by ds is equivalent to the integral from 0 to infinity d by ds acting on f of t e to the minus st dt. But as we already noted, f of t doesn't care about s either. It only depends on t. So we can go a step further and pass that derivative through until it hits the thing that it's really looking for, the e to the minus st. Now the fact that all of this is happening within an integral is completely irrelevant. The differentiation of the exponential will just go in the usual way. That means we will have f of t. We differentiate an exponential, we get the same exponential, but the chain rule tells us we must bring down the coefficient of s, which is negative t. I'm going to sandwich it in the middle there. Well, where has this got us? What we're looking at here is an exponential inside the integral, but multiplied by now not f of t, but f of t times negative t. Actually, that means that what we've got here is just the Laplace transform of the function negative t times little f of t. So let's write it that way. Well, that's very interesting. It's given us an interpretation for d capital F by ds. Actually, it's more conventional to pull the negative sign out of the integral and take it over to the other side. In that case, we will see the following form for the expression. The Laplace transform of t times f of t is now df by ds, but that negative sign has come outside there. This can be really a very useful device. Let's see an example of its use. Let's think of a simple function, say sine 3t. We know that the Laplace transform of sine 3t, we could look it up in tables, it's simply 3 over s squared plus 9. Our formula above now tells us that we could just as easily write down the Laplace transform for t times sine 3t. It must be negative d by ds acting on 3 over s squared plus 9. We need to do the differentiation. It just involves either the quotient rule or the chain rule. If we use the quotient rule, we know that we have to square the denominator. Let's just look back at what we're doing. Oh, there's that minus sign out the front. We better put that in. Now, the denominator's fixed up. The quotient rule says we now fix up the numerator by saying the bottom multiplied by what you get when you differentiate the top. The top is a constant, 3, so you won't get anything there. The quotient rule then says continue by taking the top, that's 3, multiplied by what we get when we differentiate the bottom. That'll be 2s. But remember, the quotient rule also has its own negative sign for this term. It gives us altogether 2 negatives, so we end up with 6s over s squared plus 9 all squared. Summing up, we've discovered the Laplace transform for t sine 3t is 6s over s squared plus 9 all squared. Think about what we've achieved there. If we define this Laplace transform with the usual integral, we know it's the same as the integral 0 to infinity t sine 3t e to the minus st dt. That's quite a complicated integral. It would take several steps of integration by parts to evaluate this integral in any other way. The Laplace transform has given us a very efficient method of finding this integral. Before concluding this recording, I'd like to go just one step further. What if we repeat the differentiation? What about the second derivative of capital F, or the third, or the fourth? What might that mean? Well, we could think of it this way. The Laplace transform of t f of t is minus d by ds of capital F. Using another differentiation, it seems quite likely it will be equivalent to multiplying by another t, and in fact that is the case. If we take L of t squared f of t, that's the same as L of t times t f of t, which is minus d by ds, and then another minus d by ds of capital F of s. Altogether that makes plus d2f by ds squared. In fact, for each multiple of t, we have to include an extra negative and an extra differentiation. So we could write down a formula for t to the power n times f of t. It will look something like this. We need a minus for each of the powers of t, so that will be negative 1 to the n. We also need a derivative for each power of t, so that will be the nth derivative with respect to s. This works, of course, if n is a positive integer. Before we conclude, let's see this in operation. Let's try and work out the Laplace transform of, let's say, t squared. Let's have sine t again. Let's make it just sine t though to keep the numbers simpler. What we need to do is negative 1 squared and then the second derivative of the Laplace transform for sine, which in this case is just 1 over s squared plus 1. The negative 1 squared becomes 1, so if we perform one of the differentiations using the quotient rule, we'll have the usual square of the denominator, and we'll have minus 2s on top. Then we have to differentiate again, so this time we get s squared plus 1 all to the power 4. And the quotient rule says denominator multiplied by differential of the numerator minus the numerator times the differential of the denominator. That's a fairly messy expression on top, but in principle it can be simplified and give us a sensible Laplace transform. I'll leave you to finish that simplification.